When it comes to collisions, there are two types of collisions: elastic collisions and inelastic collisions. Elastic collisions, I think about an elastic rubber band, I think about springs, I think about objects that bounce back. So an elastic collision is one in which the energy is conserved. We got very, very close to having elastic collisions with our Pasco lab collisions, where carts collided with each other with the magnetic bumpers, and that invisible magnetic bumper allowed the object to bounce back. So in all collisions, momentum is conserved, but in elastic collisions, energy and momentum is conserved. So let's look at the elastic collisions. So your momentum is going to be conserved. So it's going to obey the M1 V1 initial plus M2 V2 initial is equal to M1 V1 plus M2 V2 equation for the conservation of momentum. Now, if energy is also conserved, if an object is moving and a collision should occur in one dimension. So what do I mean by that? So if we're looking at our two Pasco cars and they collide with each other, so you've got one object here and you've got another object here, the collision occurs on this flat surface where there was no change in potential energy. There was no height change during the collision. And that's great because that means that the gravitational force is not changing, so it's technically not an external force acting on the objects. If collisions occur in midair and the gravitational force is acting on the two objects, then that can be considered an external force and our momentum is not always conserved. So when these two objects, and just for the sake of this, I'm going to pretend like these springs represent the bouncy property of having those opposite or those like poled magnets on the end. When our two carts were going towards each other, they were able to bounce off. And all of the energy of the system was momentarily transferred to the springy nature of our magnetic field system, and then they bounced back off. So there's no change in potential energy during the collision, but each object has a kinetic energy. So I could actually find the kinetic energy using our old friend 1/2 mv squared for each one of the objects before and after the collision. And so for an elastic system, I could use both the conservation of momentum and this version of the conservation of energy, but it's only kinetic energy because there are no other, there's no change in potential energy during the collision. So no need to solve for that. Height, y stays the same in both cases, or during the collision. Now, this equation down here can be kind of yucky to use sometimes. And technically I could have two unknowns because I have two conservation laws to apply to the system. And if you have two conservation laws, you can have two unknowns. So technically you could know the initial speed of each one of your objects, and you could solve for the final speed of each of the objects because we have these two equations. The whole two equations, two unknown business works. Now, applying this conservation of energy, kinetic energy equation can be ugly. So, I can do some ninja math and come up with a third short little equation to use for elastic collisions. So you do not have to be able to derive this, but I'm going to show it to you because I like doing algebra. So this is a derivation. I'm going to put a little red squiggly line across here because I'm going to start this derivation. So I'm going to solve for a third elastic equation based on these two. So what I want to do is eliminate the mass is my ultimate goal. So I'm going to look at the energy equation first. The first thing I see I can do here is simplify it by multiplying by 2 on both sides. So if I multiply that conservation of energy, conservation of kinetic energy equation right here by 2, then I would have m1 v1 naught squared plus m2 v2 naught squared is equal to m1 v1 squared plus m2 v2 squared. So that's a pretty simple little step there. Now, I want to get my m1s together and my m2s together. So I'm going to have m1 v1 naught squared minus m1 v1 squared, and then I'll have m2 v2 squared minus m2 v2 naught squared. I can factor out m1 on the left side and m2 on the right side. So again, this is not something that you have to be able to do. I just like showing you how to come up with equations and how to use all the algebra that you learned before. Okay, so I recognize this as being the difference of two squares. And if I'm remembering my algebra right, that means this is equivalent to v1 naught minus v1 times v1 naught plus v1. So think about that. See if you remember the difference of two squares. Now, as you were sitting there in algebra learning that stuff, thinking, when would I ever use this again? Well, here you go. We're using it again. So I'm kind of to an ending spot here with this energy. So this was the kinetic energy equation. Now, our conservation of momentum equation could be written as m1 times v1 naught minus v1 is equal to m2 times v2 minus v2 initial. Now if you want to, so that is the momentum of one object is equal to the change in momentum of one object is equal to the negative change in momentum of the other object. So if you want to see real quick where in the world I got this momentum equation right here, this m1 times v1 naught minus v1 is equal to m2 times v2 minus v2 naught. If we go back up here to this conservation of momentum equation, I'm going to rewrite it down here. m1 v1 naught plus m2 v2 naught is equal to m1 v1 plus m2 v2. Now again, let's get m1 on the left side. let's get M2 on the right side. Maybe you can already see how this equation right here, I'll highlight it in yellow. This equation right here could come from our conservation of momentum. So this would be V2 initial. And can I factor out an M1 and factor out an M2? So now I have this really pretty equation for the conservation of energy all factored down, and I've got this conservation of momentum equation, and they look super duper similar. So one of the ninja math tricks that you can use when solving problems is dividing these suckers by each other when they look similar. So I'm going to put a big old division line of science right here between these two. And then I'm going to get my green lightsaber and I'm going to divide by M1 on both sides. Can I cancel out an M2? Oh, and then check it out. I can cancel out that whole entire factor on both sides there. And if you notice, we're left with something super duper pretty. The initial speed of object 1, or initial velocity of object 1, plus the final velocity of object 1 is equal to the final velocity of object 2 plus the initial velocity of object 2. And if we think about adding and what that means, the sum of the speeds of the velocities of the first object should equal the sum of the velocities of the second object. And this is only for elastic. Only for elastic collisions. And this is just a little shortcut, quick equation to use for elastic collisions. It's not absolutely necessary to get the questions correct to, use it. But it's just kind of a fun, short, easy step to solve for final velocities if you have an elastic collision. Now the other kind of collision that we have is inelastic. And this is what most collisions are. Very rarely do perfect elastic energy conserved collisions actually happen. The cases where we have elastic collisions, if you remember from chemistry, the gas laws and the pressure, volume, maybe even the root mean square velocity, the kinetic theory of the particles moving inside a container. The collisions with the walls of the container and the collisions between the gas particles, molecules themselves are assumed to be pretty close to elastic. And that's pretty much where you're going to find an elastic collision. Our Pasco cars come very close to being elastic, especially for the cars where the ball bearings in the axles of the wheels are new and nice and smooth and very little friction is acting on the system. So most collisions, though, in real life are inelastic. Most collisions that you have ever experienced are inelastic. And there are varying degrees of inelastic collisions, from a collision where the objects bounce off each other and energy is not conserved during that collision, to collisions where the objects actually stick together. And so one of the most popular inelastic collisions is called the completely or totally sometimes even perfectly inelastic collisions occur. So this is when they stick together. And the opposite of sticking together is explode apart. Sometimes I think of an explosion as being like an uncollision, or then that's a total made up word by me. An uncollision, or even a recoil collision sometimes. So those are also known as the explosion. So what happens, either you've got two masses initially separate, and they are going to stick together, and by sticking together they have a common velocity. So M1 and M2 are together, and a lot of times I call their common velocity V3 because I haven't used the subscript 3 yet. That is the short answer. That is the answer. Or maybe our objects start out together in the case of an explosion like fireworks, and they're moving at a common velocity. I'm going to call V3 again, but it's the initial. And then they explode apart into two pieces or more pieces. I could have M1V1 plus M2V2 plus M3V3 plus M4V4. I hope you get the idea there. So this is when they stick together. This is when they explode apart. The doesn't matter really because which way you look at the equation, because the momentum before and after have to be equal, but the energy is not going to be conserved. Okay, the initial kinetic energy is not equal to the final kinetic energy. No, no, no. Think about an explosion. If you have two objects, let's say we have our little Pasco cars and they are on the track, and you guys seen the plungers where the spring-loaded plunger was inside the little car. If I have a second car sitting there next to it, and they are like jammed right up next to each other, what I'm talking about, and they both have their little spring-loaded plungers set inside them, and they have little buttons on top. If you press, first of all, the initial kinetic energy of that system is 0. And then if you press the button, then the after effect here, so there's my before and then afterwards, each one of our Pasco cars is zooming, totally zooming. They zoom apart. How many times did you shoot them across the table as we were looking at the lab? So each one of them then has a velocity after the collision or uncollision, the explosion. So I'll call this one V1 and this one be V2. So there is a kinetic energy of the system of 1/2 M1 V1 squared plus 1/2 M2 V2 squared. And so definitely there's a change in energy. Where do you think that energy comes from? If you think about it, our plunger was all compressed, and now our spring is all unstretched. That's an ugly spring, but anyway, our spring's all unstretched. So the gain in energy came from the energy stored in the springs inside the carts. But look at the momentum of this explosion. The initial momentum of the system was 0 because the carts are just sitting there. Is it possible for the final momentum of the objects, the final momentum, to also be 0? Our final momentum would be M times negative V1 plus m times v2. I think it's possible to have this negative value plus that positive value give you 0. So, momentum is conserved in all collisions. Energy is conserved in elastic collisions. Kinetic energy is not conserved in inelastic collisions.